In 1905, a quiet, unassuming patent clerk named Albert Einstein gave humanity the keys to time travel. No, he didn't hand us a blueprint for a shiny, chrome-plated machine with blinking lights. What he gave us was far more profound, a theoretical recipe. He proved with breathtaking elegance that time isn't a constant, unyielding force. It's a river that can be bent, slowed, and astonishingly navigated. For over a century, those keys have been sitting right there, in plain sight, waiting. So, if the recipe exists, why haven't we built the machine yet? Forget the flickering screens of Hollywood, the glowing blue portals, or the quaint, often contradictory tales of paradoxes. The real story of time travel isn't about magical devices. It's woven into the very fabric of our universe, a secret hidden within the most famous theory in all of science. And to truly grasp it, we have to rewind back to a time when everyone, from the greatest scientists to the humblest farmers, just knew how time worked. Before Einstein came along, the universe seemed so straightforward. Time, we believed, was like a grand cosmic metronome, ticking away at the exact same unchangeable rate for everyone, everywhere. Imagine it, a single colossal clock hanging in the heavens, its pendulum swinging in perfect universal rhythm. Tick-tock, tick-tock. This was the vision laid down by Isaac Newton centuries earlier, and it became the bedrock of physics, of our very understanding of existence. You see, for Newton, time wasn't something you could bend or manipulate. It was absolute. It flowed uniformly, independently of anything else. Whether you were sitting still, hurtling through space on a comet, or just stirring your morning coffee, that cosmic metronome kept its beat, indifferent to your experience. Your clock, my clock, a clock on the furthest star. They all supposedly marched in lockstep, perfectly synchronized across the vastness of creation. This was the clockmaker's masterpiece, a universe built with immutable precision, where every second was identical to the last, and every moment progressed in an orderly, predictable fashion. It was the ultimate comfort, the ultimate certainty, a universal, unyielding rhythm to which all of reality danced. This idea of absolute time permeated everything. It shaped our philosophy, our literature, our very intuition about the world. It felt so right, so self-evident. Of course, time is the same for everyone. How could it be otherwise? The sun rises, the seasons change, we age. These are universal experiences, aren't they? This rigid cosmic clockwork was the ultimate authority, dictating causality, ensuring that cause always preceded effect, maintaining the tidy order of the cosmos. But here's the thing about deeply held beliefs. Sometimes they're just waiting for someone to point out the fundamental flaw, someone to notice the tiny crack in the perfectly polished facade. And in 1905, that someone was a 26-year-old patent clerk with a penchant for asking uncomfortable questions. He looked at that magnificent universal clockwork, that cosmic metronome, and saw something no one else had dared to consider. He saw an illusion. He saw a fundamental error in the machine that governed our understanding of everything. And with a series of papers he published that year, his Annus Mirabilis, or Miracle Year, Albert Einstein didn't just tweak Newton's physics. He shattered the cosmic metronome into a million pieces. He revealed that the universal clock was a myth, that your time and my time and the time on a spaceship hurtling through the void could all be fundamentally, measurably different. He didn't just theorize this. He provided the mathematical proofs, the elegant equations that demonstrated how time, far from being absolute, was in fact relative. It was flexible, it was personal, It was something that could stretch and compress, depending on your speed. This wasn't some abstract philosophical musing. This was hard science, and the implications were, and still are, mind-bending. This wasn't a philosophical debate. It was a revelation that would fundamentally alter our understanding of the universe. Einstein showed us that the steady, unwavering tick-tock of the cosmic clock was a grand deception, a convenient fiction we'd all agreed upon. His special theory of relativity, published that year, introduced the concept of time dilation, the astonishing idea that a clock moving at high speed actually ticks slower than a stationary clock, from the perspective of an observer who isn't moving. This wasn't some theoretical edge case. This was a fundamental property of time itself. Think about that for a moment. For centuries, we were convinced time was an unyielding river, flowing at the same speed for everyone. Then, a young man, working in a patent office, proved it wasn't a river at all, but more like a current, influenced by your motion. This meant that the very moment you started moving faster, your personal clock, your experience of time, began to diverge from those who remained still. It wasn't a flaw in your clock. It was a flaw in the universal assumption of time itself. It's a concept so radical, so counterintuitive, that even today, it challenges our everyday experience. Yet, it's not just a theory. It's a proven fact. Our most advanced technologies, like the GPS satellites that guide your car every day, literally have to adjust for this relativistic effect. Without constant corrections, accounting for the fact that their clocks run slightly differently due to their speed and distance from Earth's gravity, your GPS wouldn't work, drifting by kilometers every single day. The universe is constantly proving Einstein right, even if we're not always aware of it. So, the universal clockwork, that rigid cosmic metronome, it was an illusion. And in 1905, Albert Einstein, with a stroke of genius, didn't just find a fundamental flaw in the machine. He showed us how to exploit it. He showed us that time travel wasn't just possible. It was an inherent feature of reality, waiting to be understood. But if speed could bend time, what about gravity? Could something even more fundamental than motion warp the very fabric of existence, creating even stranger pathways through time? But if speed could bend time, what about gravity? Could something even more fundamental than motion warp the very fabric of existence, creating even stranger pathways through time? Well, let's hold that thought on gravity for just a moment, because the journey to truly grasp time travel starts with what Einstein uncovered about speed itself. In 1905, during his miracle year, a young Albert Einstein, then a patent clerk in Bern, Switzerland, delivered a paper that fundamentally reshaped our reality. It was called On the Electrodynamics of Moving Bodies, and in it, he introduced us to the special theory of relativity. Before Einstein, the universe largely ran on Isaac Newton's clockwork. Time was this absolute, unwavering constant, ticking away uniformly for everyone, everywhere. A minute here was a minute there, no matter what. But Einstein shattered that illusion. Imagine time not as a rigid, unyielding track, but as a flowing river, the elastic river. Now here's the twist. Everyone is on their own boat, and everyone has their own current. The speed at which you paddle across this river, that is, how fast you move through space, directly impacts how quickly you drift downstream through time. The faster you move through space, the slower you move through time, relative to someone who is moving more slowly. This isn't a trick of perception. It's a fundamental property of the universe. Time literally slows down for you. This phenomenon, known as time dilation, means that a clock, moving at high speed, will tick slower than a stationary clock, from the perspective of an observer who isn't moving. It sounds like something straight out of a sci-fi novel, right? But it's not. It's a scientific fact, proven by countless experiments. Consider the humble muon. These are tiny, unstable subatomic particles, much like heavier electrons, constantly raining down on Earth from cosmic rays colliding with our upper atmosphere. When muons are at rest, their average lifespan is incredibly short, only about 2.2 microseconds. If you calculate how far they should travel at near light speed, in that fleeting moment, they wouldn't even make it halfway to the Earth's surface, from where they're formed. Yet, we detect vast numbers of them at sea level. So, what gives? Here's the aha moment. These muons are traveling at incredible velocities, often exceeding 99.5% the speed of light. From our perspective on Earth, their internal clocks are ticking slower. Because their time is dilated, they live much longer than they should, allowing them to traverse the vast distance from the upper atmosphere all the way down to us. Their short lifespan, which would normally only allow them to travel about 470 meters, is extended by a factor of 8 to 10 due to their speed, letting them cover kilometers. This isn't magic. It's a direct, undeniable confirmation of time dilation. And it's not just subatomic particles. In 1971, physicists Joseph Haffel and Richard Keating conducted a groundbreaking experiment. They took 4 highly precise cesium beam atomic clocks and flew them twice around the world on commercial airliners, once eastward, once westward. When they compared these flying clocks to stationary clocks at the U.S. Naval Observatory, the results were astonishingly clear. The clocks on the eastward flying plane, moving with Earth's rotation, lost 59 nanoseconds compared to the ground clocks. The westward flying clocks, moving against Earth's rotation, gained 273 nanoseconds. These tiny, almost imperceptible differences, nanoseconds or billionths of a second, precisely matched Einstein's predictions for how time would be affected by both the plane's speeds and their slight changes in altitude. The Mr. Clock even had its own seat on the plane. This wasn't some theoretical abstraction. It was a real, measurable effect on macroscopic clocks, affirming that time is indeed relative. So what does this mean for us, for humanity's greatest dream of time travel? It means that forward time travel is not just possible, it's a scientific reality. The recipe for it, given to us by special relativity, is deceptively simple. Travel at near the speed of light. Think about the famous twin paradox. Imagine 2 identical twins. Let's call them Alice and Bob. Alice stays here on Earth, living her life, experiencing time at what we consider a normal pace. Bob, on the other hand, embarks on an incredible journey. He climbs into a spacecraft capable of accelerating to, say, 99.995% the speed of light. He flies off into the cosmos, perhaps to a distant star system like Proxima Centauri, turns around, and comes back. From Bob's perspective inside the spacecraft, his journey might only take a few years. His clocks tick normally, his heart beats at its usual rhythm. He eats, sleeps, reads books, watches movies, all at a seemingly normal rate. But because he is moving at such an extreme velocity, his time is dilated relative to Alice's. For every year that passes for Bob, many, many more years could have passed for Alice back on Earth. When Bob finally returns, stepping out of his spacecraft, he would find an Earth transformed. Alice, his twin sister, would be decades, perhaps even centuries, older than him, or long gone. He would be a young man returning to a future he never lived, a future where everyone he knew might be dust. This isn't a paradox in the sense of a logical contradiction. It's an undeniable consequence of the universe's laws. The asymmetry comes from Bob's acceleration and deceleration, making his journey fundamentally different from Alice's stationary experience. He truly has traveled into his own future. This means the dream of forward time travel is already within the realm of scientific possibility, at least in theory. If we could build a spacecraft that could sustain near light speeds, we could, quite literally, send someone into the future. But there's a catch, a big one. The energy required to accelerate even a small object to such speeds is astronomical, far more than humanity has ever produced. Furthermore, as an object approaches the speed of light, its mass appears to increase infinitely, making it impossible for any object with mass to ever reach the speed of light, let alone exceed it. It's a cosmic speed limit, woven into the very fabric of existence. So, while speed offers a clear, if practically unattainable path to the future, it doesn't give us the whole picture. It shows us that time is not fixed, that it's an elastic river, bending and stretching based on how we move through it. But what if there was another way to bend that river? Not just by moving through it, but by warping the riverbed itself. Could something as fundamental as gravity provide an even more profound loophole, creating shortcuts not just through time, but through space itself? So, while speed offers a clear, if practically unattainable path to the future, it doesn't give us the whole picture. It shows us that time is not fixed, that it's an elastic river, bending and stretching based on how we move through it. But what if there was another way to bend that river? Not just by moving through it, but by warping the riverbed itself. Could something as fundamental as gravity provide an even more profound loophole, creating shortcuts not just through time, but through space itself? The answer, it turns out, is a resounding yes. And it's another gift from the mind of Albert Einstein. A decade after he unveiled special relativity, in 1915, he presented the world with his general theory of relativity. This wasn't just an update. It was a complete reimagining of gravity itself. Prior to Einstein, we thought of gravity as a force, a mysterious pull between objects. But Einstein showed us something far more elegant and far stranger. Gravity isn't a force at all. It's the curvature of spacetime. Imagine spacetime not as an empty, rigid stage, but as a vast, stretched-out trampoline. Now, picture placing a bowling ball in the center of that trampoline. What happens? It creates a deep dip, a curve in the fabric. If you then roll a marble across the trampoline, it won't travel in a straight line. It will curve inward, drawn towards the bowling ball, not by a force, but by the distortion in the trampoline's surface. That, in essence, is gravity. Massive objects, planets, stars, black holes, don't pull on us. They bend the very fabric of space-time around them, creating these gravity wells. Here's where it gets truly wild. This bending of space-time doesn't just affect how objects move through space. It also affects the flow of time. Clocks in stronger gravitational fields, closer to the bottom of these cosmic gravity wells, tick slower than clocks in weaker gravity higher up on the trampoline. This phenomenon is called gravitational time dilation. It means that if you were to spend time near a massive object, where gravity is intense, time would literally slow down for you compared to someone far away, in a region of weaker gravity. You would be traveling into the future just by standing still. This isn't some abstract theoretical idea we can only ponder in distant galaxies. It's happening right now, above your head, and it's critical to technology you use every single day. Think about your phone and how it uses GPS to tell you where you are or how to get to your favorite coffee shop. Those GPS satellites orbit Earth at an altitude of about 20,000 kilometers, moving at speeds around 14,000 kilometers per hour. Because they're moving so fast, special relativity predicts their clocks should tick a little slower than clocks on Earth. But here's the kicker. Because they're further away from Earth's massive gravitational pull, in a weaker gravity well, general relativity predicts their clocks should actually tick faster than clocks on the ground. So, which effect wins out? Both are happening simultaneously. The clocks on GPS satellites lose about 7 microseconds per day due to their speed, but they gain approximately 45 microseconds per day because they are in a weaker gravitational field. The net effect? GPS satellite clocks tick faster than ground-based clocks by about 38 microseconds per day. That might sound tiny, almost negligible, but if GPS systems didn't constantly correct for this discrepancy, your navigation would be off by roughly 11.4 kilometers every single day. Within minutes, your phone would think you were miles from where you actually were, and you'd never find that coffee shop. And it's not just GPS. In 1971, physicists Joseph Loophole and Richard Keating conducted a groundbreaking experiment that put these predictions to the test. They flew incredibly precise atomic clocks on commercial airliners around the world, first eastward, then westward. When they compared these flying clocks to identical clocks that remained stationary at the U.S. Naval Observatory, they found exactly what Einstein's theories predicted. The eastward flying clock, moving faster relative to the Earth's rotation, lost 59 nanoseconds. The westward flying clock, moving slower relative to the Earth's rotation, gained 273 nanoseconds. These tiny yet measurable differences were in perfect agreement with the combined effects of both special and general relativity, confirming that time truly is a river, and its flow can be altered by both speed and gravity. So, here's our second theoretical recipe for time travel into the future. Find a region of extremely powerful gravity. And where do we find the most extreme gravity in the universe? Near a black hole. These cosmic behemoths are born from the collapse of massive stars, crushing matter into an incredibly dense point, warping space-time so intensely that nothing, not even light, can escape their grasp once it crosses a boundary called the event horizon. If you could orbit a black hole safely outside its event horizon, you would experience time slowing down dramatically. Imagine an astronaut orbiting a supermassive black hole for what, to them, feels like a few hours or days. When they return to Earth, they might find that centuries, even millennia, have passed. From their perspective, they've traveled far into humanity's future. Of course, the practical challenges are immense. Getting close enough to a black hole to experience significant time dilation without being torn apart by its tidal forces, a process charmingly known as spaghettification, would require engineering feats far beyond our current capabilities. And the return journey, navigating back through vast interstellar distances, presents its own set of problems. But the point isn't about the how yet. It's about the if. And Einstein's theories tell us unequivocally that forward time travel via gravity is not just possible, but an inherent feature of our universe. So we have two profound ways to bend time: speed and gravity. Both offer a one-way ticket to the future, making us ponder the incredible elasticity of time itself. But what if we didn't just want to slow time down or speed it up? What if we wanted to find a genuine shortcut, a tunnel not just through space, but through time itself? Could Einstein's ultimate theory of gravity, which allows for such extreme distortions, also provide a hidden pathway to truly navigate the temporal landscape? Could Einstein's ultimate theory of gravity, which allows for such extreme distortions, also provide a hidden pathway to truly navigate the temporal landscape. Well, that's where things get truly wild and profoundly human. Because while Einstein's theories offer us these theoretical recipes for a one-way trip to tomorrow, they also lay bare the immense, heartbreaking cost of such a journey. It's a cost so deep, it makes you question if humanity would ever truly dare to pay it. Imagine for a moment two siblings, twins, born on the same day, sharing every first memory, every scraped knee, every secret whispered in the dark. Let's call them Mia and Leo. They live in a future where we've figured out how to build a ship capable of traveling incredibly close to the speed of light, not quite light speed, but close enough to make a difference, a real difference. Mia, driven by an insatiable curiosity, decides to take that leap. She's chosen for a pioneering mission, a journey to a distant star system, perhaps Proxima Centauri, just over 4 light years away. For her, the trip there and back at near light speed might only take a few years of her life. She'd see new worlds, witness cosmic wonders, and feel the thrill of pushing the boundaries of human exploration. She waves goodbye to Leo, promising to be back before he knows it. He stands there on the launch pad, a lump in his throat, watching her rocket vanish into the sky. But here's the kicker, the profound, almost cruel twist that Einstein's special theory of relativity, published in 1905, laid bare for us. Time, as he proved, isn't some universal steady drumbeat. It's a river that flows differently, depending on how fast you're moving. From Mia's perspective, inside that incredibly fast ship, her clock, her very biological clock, is ticking slower than Leo's back on Earth. The faster you move, the slower time ticks for you, compared to someone standing still. This isn't just a theoretical parlor trick. This is real, measurable physics. Think about the atomic clocks flown around the world in the 1971 Hafele-Keating experiment. They literally confirmed this. The clocks on the planes, moving at high speeds, actually measured a tiny, tiny fraction of a second less time than the clocks that stayed on the ground. It's not much for a plane trip, but it's undeniable proof. Or consider muons, tiny particles created in our upper atmosphere. They have a natural lifespan of about 2.2 microseconds. By all rights, they shouldn't live long enough to reach Earth's surface. But because they're hurtling toward us at near light speeds, their internal clocks slow down from our perspective, extending their lives, allowing them to make it all the way down. Time, literally, stretches for them. Even the GPS in your phone relies on these precise relativistic corrections every single day. Without accounting for the difference in how fast satellite clocks tick compared to ours on the ground, your navigation would be miles off within minutes. So, as Mia races through the cosmos, experiencing a few years of incredible adventure, what's happening back on Earth? For Leo and everyone else she knows, time is marching forward at its usual pace. Her few years of travel could translate into decades, even centuries, for those she left behind. Imagine Maya's return. The ship descends, a triumphant beacon against the alien sky. She steps out, still young, still vibrant, the same age as when she left. But the cheers that greet her are from strangers. The faces are unfamiliar. The city she knew is gone, replaced by towering structures she doesn't recognize. She looks for Leo in the crowd, her heart pounding with anticipation, ready to embrace her twin, to share her stories. But Leo isn't there. He's long gone. His children's 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 children have lived and died, their stories fading into the annals of history. Her parents, her friends, her entire world have dissolved into dust, their memories preserved only in archives she'll never fully grasp. The message she sent across the ocean of time, her return, has landed on a shore centuries in the future, a future completely alien to her. This is the profound, gut-wrenching aha moment of forward time travel, often called the twin paradox. It's not a paradox in the sense of a logical contradiction, but a paradox of human experience. Maya, the intrepid traveler, has achieved humanity's greatest dream. She has journeyed to the future. She is a pioneer, a living legend. But the price of seeing that future is the complete, absolute loss of her own past. Every person she loved, every familiar comfort, every cherished memory tied to a living soul is gone forever. She is physically young, a temporal orphan, adrift in a future that is hers, yet utterly foreign. The very fabric of existence that allowed her to travel forward in time has also woven a tapestry of isolation, a profound loneliness that no amount of scientific triumph can soothe. She is a message in a bottle indeed, but the sender and the intended recipient are now separated by an unbridgeable gulf of centuries. So, while Einstein's equations give us the keys to unlock the future, they also reveal a truth. The universe doesn't offer a free lunch. Every journey, especially one through the very essence of time, comes with an unimaginable cost. We can, theoretically, outrun the relentless march of time, but we can't outrun its consequences for our human connections. But what if there was another way? A genuine shortcut, not just to outrun time, but to truly navigate it. A path not just through the vast emptiness of space, but through the very fabric of spacetime itself. Could Einstein's greatest gift, his general theory of relativity, which describes gravity not as a force, but as the warping of spacetime, hold an even more audacious secret? A secret that points to tunnels through the cosmos, structures that could offer a different kind of temporal journey entirely? A journey that might, just might, allow us to return to the past, or leapfrog to a different future, without abandoning everything we hold dear. Yes, absolutely. Because Einstein's work wasn't just about slowing time down, it was about the very structure of reality itself. His general theory of relativity, published in that monumental year of 1915, didn't just describe gravity as a force pulling things down. It revealed gravity as the dynamic, pliable curvature of space-time. Think of it like this. Imagine you're holding a massive bowling ball on a stretched-out rubber sheet. That ball creates a deep dip, a significant curve. If you then roll a marble nearby, it doesn't get pulled by the bowling ball. It simply follows the curve in the sheet. That, in essence, is how gravity works. Massive objects warp the fabric of space-time, and everything else, from planets to light itself, follows those profound invisible curves. Now, let's take that metaphor a step further, because this is where the real mind-bending stuff begins to unfold. Imagine space-time not merely as a two-dimensional rubber sheet, but as a vast, infinitely complex four-dimensional map. 3 dimensions of space, 1 of time. On this map, you have 2 distant cities, say, New York and Los Angeles. Normally, to get from one to the other, you drive the long, winding roads, traversing countless miles and hours. That's how we travel through space and time conventionally, one moment after another, 1 mile at a time. But what if you could take that map, that immense expanse of space-time, and just fold it in half? What if you could bring New York and Los Angeles so incredibly close together that they literally touched? And then, what if you could punch a pencil right through that folded map, creating an instant connection, a mystical shortcut that bypasses all the arduous miles and the relentless march of time in between? That, my friends, is the awe-inspiring, almost fantastical core idea of a wormhole. A cosmic shortcut, not just through the vast emptiness of space, but through the very fabric of spacetime itself. The blueprint for these astonishing cosmic tunnels wasn't some wild sci-fi dream cooked up in a writer's room, a product of pure imagination. No, the theoretical possibility of these bridges was incredibly hidden right there, lurking within the intricate mathematics of Einstein's own equations. It was in 1935, 2 decades after his general relativity paper, that Albert Einstein, collaborating with his colleague Nathan Rosen, first theorized these structures. They called them Einstein-Rosen bridges. The more evocative term wormhole itself wouldn't be coined until 1957 by the brilliant physicist John Archibald Wheeler. But the concept, the astonishing idea of a natural warp in reality, was born from Einstein's genius, a hidden loophole in the cosmic rules. So, what exactly is an Einstein-Rosen bridge? Picture it, if you can, as a theoretical tunnel connecting 2 disparate points in spacetime. It could link 2 distant regions within our own universe, offering a way to traverse light years in moments. Or, even more mind-bendingly, it could theoretically connect 2 entirely different universes. Imagine collapsing a star into a black hole. The intense gravity warps space-time so severely, creating a profound pit. An Einstein-Rosen bridge is like having 2 of these intensely warped regions connected by a narrow throat or a tunnel. It's a bit like having 2 funnels, wide at the top and narrow at the bottom, and then connecting their narrow ends. The entrance and exit could be light years apart, but the journey through the wormhole itself would be incredibly short, perhaps even instantaneous for the traveler. This is the ultimate aha moment for interstellar travel, promising to make the impossible possible. But here's the rub, the crucial what if that takes us from theoretical possibility to practical impossibility, at least for now. While Einstein and Rosen's initial math showed these bridges could exist, their models described them as non-traversable, meaning they would likely pinch off and collapse the moment anything, even a particle of light, tried to pass through them. It's like trying to walk across a bridge made of pure thought. It's there one moment, gone the next, taking any hopeful traveler with it. For a wormhole to be a true pathway, a cosmic highway for you to be able to actually journey through one, without being crushed into oblivion, it needs something special, something extraordinary, to hold its throat open. And that's where the deeply intriguing, yet profoundly challenging concept of exotic matter comes in. This isn't just some made-up stuff from a sci-fi movie. It's a theoretical substance with truly bizarre, counterintuitive properties. To keep a wormhole open, to act as that stable cosmic scaffolding, it would need to possess negative energy density. Think about that for a second. Everything we normally interact with, every atom, every star, every galaxy, has positive energy. But exotic matter, if it exists in sufficient quantities and can be harnessed, would essentially push space-time apart rather than pulling it together. It would exert a repulsive gravitational effect, preventing the wormhole from collapsing. Now, before you dismiss this as pure fantasy, let me tell you that negative energy isn't entirely unheard of in physics. We've actually observed its effects in the quantum realm, in phenomena like the Casimir effect. This is where 2 uncharged parallel conductive plates are placed very close together in a vacuum, and they experience a slight attractive force. This force is attributed to the difference in quantum vacuum fluctuations between the plates, which can be interpreted as a region of negative energy density. The problem is, the amounts we've observed are minuscule, microscopic. To hold open a wormhole large enough for a spaceship, let alone a human being, would require immense quantities of exotic matter, far beyond anything we can currently imagine, let alone create or harness. Theoretical calculations often involve densities and pressures that are far beyond any currently achievable technology. This is the ultimate cosmic quest, finding and mastering the key ingredient to unlock the universe's greatest shortcut. But let's allow ourselves to dream, shall we? Let's assume, for a moment, that humanity, against all odds, does figure out how to gather and stabilize this exotic matter. What then? How does a wormhole, a mere shortcut through space, become a machine for time travel? This is where the physics gets truly elegant, truly mind-bending, and our understanding of time dilation comes full circle. Remember our discussion about how time slows down for objects moving at near the speed of light or in intense gravitational fields. Well, you could, theoretically, use that very principle to turn a traversable wormhole into a time machine. Here's how this cosmic temporal manipulation might work. Imagine you have two mouths of a single wormhole. Let's call them mouth A and mouth B. You leave mouth A stationary, right here on Earth, perhaps humming away in orbit. But then, you take mouth B and accelerate it to an incredibly high speed. Let's say, very, very close to the speed of light. And then, after a period, bring it back to Earth. Because mouth B has been traveling at relativistic speeds, experiencing the full force of special relativity, time would have passed more slowly for it, compared to mouth A. This is exactly like our twin paradox, but applied to the ends of a wormhole, creating a tangible, measurable time difference between the two portals. When mouth B returns and is reunited with mouth A, it would be younger than mouth A, even if only by a few hours, days, or years, depending on the speed and duration of its journey. A temporal difference would have been created between the two ends of the wormhole. Now, if you were to step into the younger mouth B and emerge from the older mouth A, you would have traveled into the past of mouth A. Conversely, stepping into mouth A and emerging from mouth B would take you into the future of mouth B, relative to when it was accelerated. It's not about traveling through time within the wormhole itself, but about using the wormhole as a fixed pathway between 2 points in spacetime that have diverged in their temporal experience. It's like creating a permanent bridge between now and then. This isn't just idle speculation or the fevered imaginings of a screenwriter. Esteemed physicists, including Nobel laureate Kip Thorne, have rigorously calculated the physics of how such a traversable wormhole could function, even detailing the requirements for its stability and how one could, in theory, generate the temporal difference needed for time travel. Thorne, in fact, was the scientific consultant for Carl Sagan's novel Contact, and later for the critically acclaimed film Interstellar, ensuring their depictions of wormholes were as scientifically grounded as possible. He showed that such a structure, if stable and infused with exotic matter, could indeed connect different points in spacetime, potentially including different moments in time, bending the very fabric of existence to our will. Imagine the visually stunning sequence of a photorealistic wormhole traversal, emphasizing the extreme gravitational lensing and visual distortions rather than just a simple tunnel. It would be a journey unlike any other, challenging every perception of reality you hold. But there's a critical caveat, a fundamental limitation to this magnificent cosmic shortcut. You could only ever travel back to a time after the wormhole time machine was initially created. This means you couldn't build a wormhole today and then use it to go back and witness the dinosaurs or meet your great-grandparents. You could only travel back to the moment the two mouths of the wormhole were first established and accelerated. It prevents many of the classic grandfather paradoxes. You couldn't go back and prevent your own birth because the wormhole wouldn't have existed then. This limitation is a subtle yet profound safety net, seemingly built into the very fabric of physics, a kind of cosmic censorship. Even with this limitation, the idea is breathtaking. It means that the universe, through Einstein's equations, might actually offer us a pathway, a hidden door to the past. But it's a door guarded by an almost insurmountable challenge: the need for exotic matter, a substance we barely understand, let alone know how to create or control, in the vast quantities required to build such a cosmic bridge. This is the quest for exotic matter, a narrative where humanity knows the recipe, but lacks the key ingredient. So, are we truly on the cusp of folding the map of space-time? The theoretical framework is there, a gift from Einstein himself, refined and explored by generations of brilliant minds, like Kip Thorne. We have the recipe, meticulously written in the language of mathematics, but we are still missing the key ingredient. Humanity is left staring at the cosmic cookbook, understanding the instructions, but without the means to gather the necessary components. It's a tantalizing, frustrating reality, isn't it? The universe whispers its secrets, offering us glimpses of wonders like wormholes, yet demands an almost impossible price for entry. It leads us to ask, what if there are forces at play, deeper laws of nature, that actively prevent us from truly manipulating time? What if the universe itself has a chronology protection agency that steps in to prevent paradoxes, to keep the past inviolate? Stephen Hawking, for one, certainly thought so, proposing his chronology protection conjecture. Are we destined to forever gaze upon these blueprints, or will we one day find a way to truly fold the map? Are we destined to forever gaze upon these blueprints, or will we one day find a way to truly fold the map? This brings us to the ultimate hurdle, the true price of passage. For anyone hoping to step through a wormhole, to truly bend time to their will. While Einstein's equations lay out the theoretical possibility, they also reveal a monumental catch, a cosmic bouncer at the door of space-time. Imagine for a moment you're trying to dig a tunnel, not through solid rock, but through a colossal sand dune. The sand, representing the very fabric of space-time, is constantly trying to collapse inwards. You dig, you scoop, but the walls keep caving in. To keep that tunnel open, you wouldn't just need strength, you'd need some kind of magical anti-sand, a substance that, instead of being pulled down by gravity, somehow pushes outward. Something with negative mass, negative energy. That's precisely the challenge we face with wormholes. The universe, you see, is built on a simple, yet profound principle. Everything attracts everything else. Gravity, as Einstein taught us, isn't just a force pulling apples to the ground. It's the curvature of space-time itself, caused by mass and energy. Massive objects create dips and valleys in this cosmic fabric, and other objects roll towards them, giving us the sensation of gravity. This universal attraction means that any theoretical wormhole, a shortcut through space-time, would naturally want to pinch itself shut, almost instantaneously, like those sand walls collapsing. It would be a fleeting, microscopic flicker, gone before anything, even light, could pass through. For a wormhole to be traversable, for you or me to actually step inside and emerge somewhere else, or somewhen else, it needs to be held open. And the only known theoretical way to do that is with something physicists call exotic matter. Don't let the name fool you. It's not some sparkly alien crystal. It's matter that possesses negative energy density. Think about that for a second. Negative energy. It's as mind-bending as the idea of time itself being relative. Normal matter, everything you touch, see, and feel, has positive energy, contributing to the universe's tendency to collapse. Exotic matter, on the other hand, would effectively push space-time apart. It would have anti-gravitational properties, generating a repulsive force strong enough to counteract the immense gravitational pressures sealing a wormhole shut. It would be the ultimate cosmic scaffolding. Now, this isn't just wild speculation cooked up by Hollywood writers. Nobel laureate Kip Thorne, the brilliant mind behind the scientific accuracy of films like Interstellar, was one of the key physicists who rigorously calculated the exact properties this exotic matter would need. He showed that if you could somehow acquire and deploy enough of this negative energy stuff, you could, in principle, create and sustain a stable, traversable wormhole. His work, initially for Carl Sagan's novel Contact, proved that the concept wasn't just fantastical, but something rooted in the very equations of general relativity. But here's the kicker. Where do we find such a thing? Where do we get this anti-sand? The good news, and this is where it gets truly fascinating, is that negative energy isn't just a theoretical fantasy. It has actually been measured in laboratories, albeit in incredibly tiny, fleeting amounts. It's a phenomenon known as the Casimir effect. Picture 2. Uncharged, perfectly parallel metal plates, placed extremely close together in a vacuum. According to quantum mechanics, even a vacuum isn't truly empty. It's seething with virtual particles, constantly popping into and out of existence. However, between those two plates, only virtual particles with wavelengths that fit perfectly can exist. Outside the plates, there are no such restrictions. This imbalance creates a pressure differential, pushing the plates together. This tiny, measurable force is actually generated by a region of space between the plates that has a net negative energy density compared to the space outside. It's a whisper, a fleeting shadow of what we need. But it's proof that negative energy, in some form, exists within the laws of physics. It's like finding a single grain of magical anti-sand on a vast beach. The sheer scale required to create a traversable wormhole is mind-boggling. Theoretical calculations suggest that the negative energy density needed would be immense, far beyond anything we can currently conceive of generating or containing. To hold open a wormhole large enough for a spacecraft, you'd need the energy equivalent of many stars, concentrated into a tiny, stable bubble of exotic matter. It's an energy budget that makes accelerating a shuttle to near light speed, which itself would require more energy than humanity has produced in its entire history, look like child's play. So we have the blueprint, we know the properties, and we even have tantalizing hints that the fundamental ingredient, negative energy, exists. But the practical challenge remains staggering. It's the difference between understanding the principles of flight and building a rocket that can reach the stars. Yet, the idea of bending spacetime, of manipulating the very fabric of existence to create shortcuts, isn't entirely foreign to us. We live with the effects of spacetime manipulation every single day, even if we don't realize it. Take your GPS, for example. That little device in your car or phone that tells you exactly where you are, down to a few feet, relies entirely on Einstein's theories of relativity. Without them, it would be useless and fast. Here's how wild it gets. The satellites orbiting Earth, which make GPS possible, are moving at about 14,000 kilometers per hour. According to special relativity, their clocks tick slightly slower than clocks on Earth because of their speed. It's a tiny effect, about 7 microseconds slower per day. But then, there's general relativity. Those satellites are also further away from Earth's massive gravitational pull, which means their clocks tick slightly faster than clocks on the ground. This effect is much larger, about 45 microseconds faster per day. When you combine these two relativistic effects, the net result is that the clocks on GPS satellites run faster than ground-based clocks by about 38 microseconds per day. 38 millionths of a second. Sounds negligible, right? Wrong. If those tiny differences weren't corrected, if the GPS system didn't constantly account for Einstein's bending of time, your navigation would accumulate errors at a rate of about 11.4 kilometers per day. Think about that. Your phone would tell you you're in the next town over when you're just trying to find your local coffee shop. This isn't just theoretical physics for eggheads in labs. It's concrete, measurable reality that impacts your daily commute. The 1971 Hoffele-Keating experiment literally flew atomic clocks around the world on commercial airliners, proving these effects with stunning precision. The clocks flying eastward lost 59 nanoseconds, and those flying westward gained 273 nanoseconds compared to a stationary clock, exactly as Einstein predicted. And it's not just clocks. Unstable particles called muons, with a natural lifespan of about 2.2 microseconds, are observed to live significantly longer when traveling at near light speed, a direct and undeniable confirmation of time dilation. Time literally slows down for them. These aren't loopholes, they are fundamental properties of the universe. They are Einstein's keys, unlocked and utilized, allowing us to travel forward in time relative to a stationary observer, simply by moving fast or being near a strong gravitational field. The twin paradox, that heart-wrenching thought experiment, isn't just a paradox. It's a scientific prediction that has been repeatedly confirmed by experimental evidence. One twin travels to space at near light speed, experiences only a few years, returns to find their Earth-bound twin decades, or even centuries older. It's a poignant illustration of loss, sacrifice, and the profound relativity of experience. So, forward time travel, in a very real physical sense, is not just science fiction. It is a feature of our universe that we already exploit, even if subtly. But what about traveling backward? That's where wormholes become truly indispensable, and where the demand for exotic matter becomes an almost insurmountable barrier. A traversable wormhole, once created, could theoretically be manipulated to become a gateway to the past. By accelerating one mouth of the wormhole to near light speed and then returning it, that particular mouth would have experienced less time due to time dilation, creating a temporal difference between its two ends. Step through one way, you go to the future. Step through the other, you go to the past. However, there's a crucial limitation. You couldn't travel back to a time before the wormhole itself was created. The time machine's existence is tied to its creation event. So, no going back to meet dinosaurs or prevent historical mistakes that predate our advanced physics. The universe, in its wisdom, seems to build in its own safeguards against easy paradoxes. This quest for exotic matter, this search for the anti-sand to hold open our cosmic tunnel, is the true frontier of time travel. It's a narrative of scientific struggle, of relentless pursuit against seemingly impossible odds. We know the recipe. We've glimpsed the ingredients, but the kitchen, for now, remains beyond our reach. Is it a permanent barrier, a fundamental law that prevents us from ever truly turning the page of time? Or is it merely a technological challenge, waiting for a breakthrough, a new understanding of quantum mechanics, or an unforeseen discovery that will give us access to the universe's most elusive building block? What if, one day, we do find a way to harness enough negative energy? What then would be the true cost, not just in resources, but in the very fabric of our understanding of cause and effect? What would it mean for humanity to truly become unstuck in time? What would it mean for humanity to truly become unstuck in time? The very thought sends a shiver down the spine, doesn't it? Because if we could step into yesterday, if we could pluck a single thread from the tapestry of our past, what would stop the whole thing from unraveling? This is where we confront the ultimate logical tripwire of past time travel, the grandfather paradox. Imagine the timeline like a single mighty river, flowing steadily from its source to the vast ocean of the future. Every event, every decision, every breath you've ever taken is a drop in that river, contributing to its inevitable course. Now, what if you could build a machine, step into it, and travel upstream back to the very source? Let's say you journey to a time before your own parents were even born. You find your grandfather, a young man full of life, perhaps just about to meet your grandmother. And then, you do the unthinkable. You prevent that meeting. Or, in the classic chilling example, you kill your own grandfather. What happens then? If your grandfather never meets your grandmother, your parent is never born. If your parent is never born, you are never born. And if you are never born, how could you have traveled back in time to kill your grandfather in the first place? The logic loops in on itself, an impossible knot. You exist to prevent your existence. The river in this scenario has been dammed at its source, and the water you came from simply cannot exist. It's a complete logical collapse, a paradox so profound, it seems to seal the door on past time travel forever. For decades, this paradox has been the favorite weapon of skeptics, the ultimate argument against ever visiting history. Even Stephen Hawking, a titan of theoretical physics who gave us so much insight into black holes and the very fabric of spacetime, was deeply skeptical of past time travel. He proposed what he called the chronology protection conjecture in 1992, suggesting that the laws of physics themselves might conspire to prevent time travel to the past on macroscopic scales. He imagined a sort of cosmic censorship, a fundamental rule woven into the universe that would stop any attempt to create such a paradox, protecting the timeline from being broken. It's almost as if the universe has a built-in bouncer, making sure no one gets to mess with the past. But what if Hawking, brilliant as he was looking at the river from the wrong angle? What if the universe isn't a single, unalterable river at all? What if, instead, when you dam the source, the water doesn't disappear, but simply forces itself to carve a new, entirely separate river channel? This is where things get truly mind-bending, where the rigid logic of the grandfather paradox meets the wild, probabilistic world of quantum mechanics. Prepare for an aha moment that could redefine everything you think you know about reality itself. The potential solution to the grandfather paradox doesn't come from Einstein's relativity directly, but from another corner of physics, a place where reality itself seems to split and multiply. The many worlds interpretation of quantum mechanics, first proposed by physicist Hugh Everett III in 1957. This interpretation suggests something truly radical. It says that every time a quantum event occurs, every time a possibility becomes a reality, the universe doesn't just pick one path. Instead, it splits, creating new parallel universes for every possible outcome. Think about it this way. In quantum mechanics, a particle can exist in multiple states at once until it's observed. It's like a coin spinning in the air. It's neither heads nor tails until it lands. According to the many worlds interpretation, when that coin lands, it doesn't just become heads or tails. It becomes heads in one universe and tails in a separate, parallel universe. Both possibilities happen, just not in the same reality you're currently experiencing. Now, apply this dizzying idea to time travel. What if you journey back in time, not to your original past, but to the past of a newly created parallel universe. You could go back, find your grandfather, and prevent him from meeting your grandmother. In the specific timeline, your parent would never be born, and consequently, you would never be born. But the you who traveled back in time, the you who originated from a different, unaltered timeline, would still exist. You haven't erased your own history. You've simply created a brand new one for a brand new universe. In this garden of forking paths, as some like to call it, changing the past doesn't create a paradox because it doesn't erase your history. It just means you're no longer in your original timeline. You've jumped tracks. You've carved that new river channel. The river you came from continues to flow, undisturbed, in its own reality. But now there's another river, branching off from that moment of intervention, where events have taken a different course. Imagine the emotional weight of that. You go back, you fix a mistake, you save a loved one, you right a historical wrong. But the people you saved, the events you altered, exist in a different universe from the one you left behind. You might have changed a past, but not your past. The original universe, with all its joys and sorrows, its triumphs and tragedies, remains precisely as you left it. You become a traveler between realities, a ghost in the machine of existence, forever separated from your true home, yet having forged a new one. This concept, while wild, offers a profound elegance to the time travel conundrum. It means that the universe is robust enough to handle our meddling. It doesn't collapse, it simply expands. Every potential paradox, every alternate choice, every different path taken, simply leads to a new branch, a new reality. The number of these universes, according to the many worlds interpretation, would be unimaginably vast, perhaps infinite, constantly splitting with every quantum decision, every moment of uncertainty. This isn't just a convenient sci-fi plot device. It's a serious contender in the scientific community for interpreting the strange nature of quantum reality. While it's still a hotly debated topic among physicists, it provides a theoretical framework where even the dreaded grandfather paradox loses its bite. The implications are staggering. If time travel to the past were ever achieved, and the many worlds interpretation holds true, then every journey would not just be a trip through time, but a leap into an entirely new dimension of existence. So, if we could find the exotic matter to hold open a wormhole, if we could accelerate one mouth to near light speed, creating that temporal gateway, we might not be breaking the universe after all. We might just be expanding it, creating new histories, new futures, with every temporal step we take. But what would it feel like to step into a past that is both familiar and utterly alien? And how would we ever find our way back home if home itself has become just one of an infinite number of possibilities? But what would it feel like to step into a past that is both familiar and utterly alien? And how would we ever find our way back home if home itself has become just one of an infinite number of possibilities? It's a dizzying thought, isn't it? This journey we're on, exploring Einstein's legacy, has shown us that time travel isn't just the stuff of late-night movies. It's written into the very fabric of space-time, a theoretical possibility woven into the universe's grand design. We've seen the blueprints for how it could work, laid out in the elegant equations of relativity. Bend space-time with immense gravity, accelerate to near the speed of light, perhaps even punch a shortcut through a wormhole. The scientific recipes are there, tantalizingly close, yet we haven't built the machine. For all the mind-bending possibilities, the logical gymnastics needed to navigate paradoxes, and the sheer technological hurdles we face, there's another far more fundamental question that has haunted the greatest minds in physics. It's a question that asks, though, not just if we can travel through time, but if the universe itself would even let us. Because what if the cosmos has its own built-in safeguards? What if, despite our best efforts, the laws of physics themselves conspire to prevent us from ever messing with the past? This brings us to one of the most brilliant and enigmatic figures of our time, a man who pushed the boundaries of our understanding of black holes, gravity, and the very nature of existence itself, Stephen Hawking. Even as he delved into the quantum intricacies of space-time, Hawking remained profoundly skeptical about time travel to the past. He wrestled with the implications, with the sheer chaos that could erupt from even a single ill-advised trip back through the calendar. And from that wrestling match, he proposed what he called the chronology protection conjecture in 1992. It's a mouthful, I know, but the idea behind it is profoundly simple and utterly captivating. Imagine the universe, not just as a collection of stars and planets, but as an incredibly complex, finely tuned computer program. Every law of physics, every fundamental constant, every particle interaction, they're all lines of elegant, intricate code. This cosmic program runs forward, constantly calculating the future based on the present. It allows information to flow, experiences to unfold, and causality to maintain its iron grip. Cause before effect, always. But what if, deep within that code, there's a built-in firewall, a fundamental, unshakable rule that prevents any user, any time traveler, from going back and corrupting the source code of reality itself? That's the essence of Hawking's chronology protection conjecture. It suggests that the laws of physics, at some deep, as yet undiscovered level, actively prevent the formation of what are called closed time-like curves. These are the theoretical pathways in space-time that would allow a person or information to travel back to their own past. In simpler terms, the universe itself acts as a cosmic censor, vigilant against any attempt to rewrite its own history. It's like an unseen guardian, silently ensuring that the timeline remains coherent, safe from the meddling hands of future beings. Hawking wasn't just speculating wildly. He was building on the very foundations Einstein laid. Einstein's general relativity, the theory that tells us how gravity warps space-time, does indeed allow for the mathematical possibility of these closed time-like curves. They emerge from the equations under extreme conditions, like those found within rapidly rotating black holes, or, as we've discussed, with certain configurations of traversable wormholes. But just because something is mathematically possible doesn't mean it's physically probable, or even permissible, by the universe's deeper, unwritten rules. Think about it this way. The universe has already shown us its preferences. We can travel into the future all the time. Every second you live, you are time traveling into your future. More dramatically, if you were to fly in a spaceship near the speed of light for a few years, then return to Earth, you would have aged less than those who stayed behind. That's not science fiction. It's a proven fact of special relativity, confirmed by countless experiments, even something as simple as the atomic clocks on GPS satellites. These satellites, zipping around Earth, experience time dilation due to their speed and their distance from Earth's gravity. Without constant corrections, their clocks would be off by about 38 microseconds a day, leading to navigational errors of kilometers. The Keating experiment in 1971 even flew atomic clocks around the world on commercial airliners, proving that time genuinely slows down or speeds up depending on your relative motion and gravitational environment. The universe allows forward time travel. It embraces it. But what about backward? Hawking famously, and rather wittily, once posed a question that has since become a cornerstone of this debate. If time travel is possible, where are the tourists from the future? At first glance, it sounds like a clever joke, a rhetorical flourish to dismiss the whole idea. But Hawking, ever the deep thinker, wasn't just trying to be funny. He was transforming a casual observation into a profound scientific argument. Their absence, he posited, isn't just a lack of evidence for time travel. Their absence is the evidence for the chronology protection conjecture itself. If time machines were ever invented, even far in the distant future, and if the universe truly had no objection to us zipping back to the past, wouldn't we expect to see some evidence? A fleeting glimpse? A mysterious artifact? A selfie with a dinosaur, perhaps? But no. Our present, our past, seems remarkably untouched by visitors from tomorrow. This quiet, unbroken flow of history, devoid of temporal meddlers, might just be the most compelling piece of observational data we have for Hawking's cosmic firewall. It suggests that if time travel to the past is theoretically possible, according to some equations, there must be some other, more fundamental law of physics that kicks in to prevent it from ever actually happening on a macroscopic scale. What would such a firewall look like, you ask? How would the universe enforce this chronology protection? Well, there are several theoretical possibilities, each more mind-bending than the last. One idea is that any attempt to create a closed, time-like curve, whether through a wormhole or some other space-time distortion, would immediately trigger a cascade of quantum fluctuations. These fluctuations, amplified by the very attempt to violate causality, would grow exponentially, creating an immense surge of energy that would instantly destroy the time machine, or perhaps even the region of space-time around it, before any paradox could form. It's like the universe saying, "Nope, not on my watch." Another possibility connects back to the very recipe we discussed for traversable wormholes: the need for exotic matter with negative energy density. While quantum mechanics does allow for tiny, fleeting instances of negative energy, the vast, stable quantities required to hold open a wormhole large enough for a person to pass through remain purely hypothetical. What if the universe simply makes it fundamentally impossible to gather or maintain such exotic matter in the necessary amounts? What if the impossibility of finding enough negative energy isn't just a technological hurdle, but a feature of the cosmic firewall itself? A subtle, elegant way to prevent us from ever reaching the source code of time. It's almost as if the universe allows us to glimpse the theoretical path to time travel, to understand the mathematics behind it, to dream the dream. But then, at the very precipice of making it real, it pulls the rug out from under us. The very conditions required for time travel might be inherently unstable, or might simply demand a form of matter or energy that the universe, in its wisdom, has deemed off-limits for tampering with the past. This isn't to say that all physicists agree with Hawking's conjecture. Like any profound idea in theoretical physics, it's debated, challenged, and explored. Some theories, like the Novikov self-consistency principle, propose that if you could travel to the past, you simply couldn't change it. Any actions you took would already be part of the timeline, preventing paradoxes from ever occurring. But Hawking's elegant solution, the chronology protection conjecture, offers a different kind of reassurance: that the universe is fundamentally stable, that its history is unalterable, and that the past is, quite literally, set in stone. It's a powerful thought, isn't it? That even with all of Einstein's genius, all the theoretical loopholes his equations revealed, there might be an even deeper unspoken law governing the cosmos, protecting its integrity. It forces us to reconsider humanity's greatest dream. Is time travel to the past a forbidden fruit, forever beyond our grasp, not because we lack the ingenuity, but because the universe itself has drawn a line in the sand. And if that line truly exists, what does it mean for our relentless drive to explore, to push boundaries, and to unravel every last secret of the cosmos? That's the question, isn't it? The one that hangs in the air, echoing through the corridors of time itself. If the universe truly has a cosmic censor, a silent protector of its past, then where does that leave us, humanity, with our insatiable curiosity and our burning desire to touch the untouchable? For over a century, we've held these keys. Albert Einstein, a man who peered deeper into the fabric of reality than perhaps anyone before him, didn't just tell us time was relative. He showed us the blueprints. He laid out the fundamental physics, the theoretical recipes for bending time, for stretching it, for creating pathways through it. He gave us the keys to a door we'd only ever dreamed of, a door to time travel itself. Imagine for a moment those keys in your hand. They gleam with the promise of impossible journeys. What do they look like? Well, for one, they look like speed. Einstein's special theory of relativity, unleashed upon the world in 1905 during his miracle year, told us that time isn't some universal steady drumbeat. Oh no, it's a river, and that river slows down for those who travel fast. We call it time dilation. If you could hop into a spaceship and accelerate to near the speed of light, say 99.995% the speed of light, your clocks would tick slower than those back on Earth. You'd embark on a journey that felt like a few years to you, only to return to an Earth where decades, even centuries, had passed. It's not just theory. It's a verified phenomenon. Think about our GPS satellites orbiting far above us. Their clocks, because of their speed, run slower by about 7 microseconds a day. And those tiny shifts, they're real, measurable, and absolutely critical for your navigation apps to work. Without constant correction for these relativistic effects, your GPS would accumulate errors of about 11.4 kilometers every single day. Einstein's physics isn't just theoretical. It's woven into the very fabric of our modern lives. Another key looks like gravity, heavy and profound. 10 years after special relativity, in 1915, Einstein unveiled his general theory of relativity. This wasn't just about speed, it was about mass, about how massive objects like planets and stars actually warp the very fabric of spacetime around them. And where gravity is stronger, time slows down. This is gravitational time dilation. Again, our GPS satellites are a perfect example because they're further away from Earth's strong gravitational pull. Their clocks actually run faster by about 45 microseconds a day. The net effect? A difference of 38 microseconds per day that must be corrected, proving that time is indeed a river bent by the celestial bodies themselves. And then there's the third key, perhaps the most alluring and perplexing of all, the wormhole. Or, as Einstein and Nathan Rosen first theorized in 1935, an Einstein-Rosen bridge. Imagine a shortcut, a cosmic tunnel that punches through the vast distances of space-time, connecting two far-flung points in an instant. The mathematics of general relativity allows for such structures. They are theoretically gateways, not just across space, but potentially across time itself. Think of a piece of paper representing space-time. 2 points are far apart. Fold the paper, and suddenly they're right next to each other. A wormhole would be the pencil poked through that fold. So, the keys exist. The theoretical recipes are there, sitting right within Einstein's most profound insights. For a century, we've been studying these keys, examining their intricate cuts, understanding their potential. We believe the door isn't sealed shut. The science isn't saying no. It's saying how. But here's the rub, the heart of the unwritten page. Those keys fit a lock, and that lock is incredibly complex. The engineering and ethical hurdles standing between us and actual time travel are immense. They represent the great quest for the next generation of pioneers, for you. To open that wormhole door, for instance, to make it traversable, meaning you could actually pass through it without it collapsing, we need something truly extraordinary. Exotic matter. This isn't your everyday kind of matter. It's matter with negative energy density, something that pushes spacetime apart rather than pulling it in. We've seen hints of it in the quantum world, in phenomena like the Casimir effect, but only on the most minuscule scales. To create a stable, human-sized wormhole would require quantities of this exotic matter and pressures that are currently beyond anything we can conceive, let alone achieve. It's like knowing you need a specific, magical ingredient for a feast, but that ingredient only exists as a whisper in the wind. And even if we could somehow conjure exotic matter, the energy required for any form of relativistic time travel is astronomical. To accelerate even a shuttle-sized object to near light speed would demand more energy than humanity has ever produced in its entire history. We're talking about scales of power that make our current global energy output look like a flickering candle in the face of a supernova. So, we stand at a precipice. Einstein gave us the blueprints, the profound understanding that time is not immutable. He showed us that the universe itself contains mechanisms for its manipulation. But the tools to enact those blueprints, the materials to build these incredible machines, the sheer power to bend the cosmos to our will, those are the challenges that remain. These are the unwritten pages of human history, waiting for someone to pick up the pen. The dream of time travel, then, is not just about building a machine. It's about something far more fundamental, far more deeply human. It's about our relentless drive to overcome our limitations, to defy the boundaries of what seems possible. It's about that quiet, universal ache, to mend our regrets, to revisit lost moments, to whisper one more word to someone gone too soon. And perhaps, most profoundly, it's about our insatiable desire to know what lies beyond the horizon of now, to glimpse the future, to understand the full sweep of our cosmic story. This isn't a story of failure. It's a story of an unfinished symphony, a quest just beginning. It's a call to a cosmic adventure, a challenge laid down by the universe itself. The theoretical path is clear, illuminated by Einstein's genius. The practical path, however, is overgrown, shrouded in mystery, and waiting for the next generation of pioneers to clear the way. It waits for you. Will we be the ones to finally turn those keys in the lock? Will humanity, driven by its deepest yearnings and its most audacious intellect, ultimately build a bridge across time? Or is there a deeper truth, a fundamental rule of the cosmos, that will forever keep the past just out of reach, preserving its sacred, unalterable history? The answers, my friend, are still out there, etched into the very fabric of space-time, waiting for us to discover them. What part will you play in writing the next chapter of this cosmic quest? If you found yourself captivated by the mysteries of time and space, then you're one of us. Join the Celestial Enigmas family by hitting that subscribe button and ringing the notification bell. Let's explore the universe's greatest secrets together. The universe, my friend, is a master of surprises. Just when you think you've grasped its rules, it unveils a deeper layer, a more profound truth that reshapes everything you thought you knew. We've journeyed through the astounding possibilities of time dilation and the mind-bending concept of wormholes, all thanks to Albert Einstein's revolutionary insights. But what if the very concept of traveling through time in the way we usually imagine it, is fundamentally flawed. What if time itself isn't what we perceive it to be at all? For most of human history, we've pictured time as a river, relentlessly flowing from the past through the present and into an uncertain future. We are, in this view, tiny boats, carried along by its current, unable to turn back or leap forward. It's an intuitive idea, one that feels deeply personal and undeniable. Every sunrise, every fading memory, every moment we anticipate, reinforces this feeling of time's relentless march. But Einstein's theories, the very foundation of our journey into time travel, quietly whisper a different, far more radical story. They suggest that time doesn't flow, not in the way a river flows anyway. Instead, they imply a concept known as the block universe. Imagine for a moment that all of time, every single moment that has ever been, is, or ever will be, exists simultaneously. It's not a sequence of events unfolding one after another, but a vast, static landscape. Think of it like a colossal four-dimensional block, where past, present, and future are all equally real, laid out in space-time, like frames in a film reel that all exist at once, even if we only perceive them sequentially. This isn't just some abstract philosophical musing. It's an implication that emerges directly from the mathematics of special and general relativity. Remember how Einstein showed that time is relative, not absolute? How two observers moving at different speeds or in different gravitational fields will experience time passing at different rates. If your now is different from my now, then the idea of a universal flowing present moment starts to unravel. It suggests that all moments are equally valid, equally real, just viewed from different perspectives within this cosmic block. Consider the elegance of this idea. If you were to travel at near the speed of light, as we explored with the twin paradox, your clock would slow down relative to someone on Earth. From your perspective, you might experience only a few years, while centuries pass on your home planet. This isn't just an illusion. It's a real physical effect, demonstrated by everything from GPS satellites, which must correct for relativistic effects to function accurately, to the observed extended lifespan of muons traveling at high speeds. But in the block universe model, you aren't skipping time. You're simply traversing a different path through the static space-time block, experiencing a different slice of its eternal existence. The future for those on Earth already exists, and your journey merely takes you to a different point on that pre-existing timeline. It's a truly mind-bending thought, isn't it? If the past, present, and future are all already there, then what does it mean to travel through time? Are we truly changing anything? Or are we simply illuminating a path that is already laid out, an immutable sequence of events that we are destined to witness? If all moments are eternally fixed, does free will, as we understand it, truly exist? Or are our choices merely part of this grand, preordained tapestry? This perspective shifts the entire conversation around time travel. It moves us away from the idea of altering history or visiting a future that is yet to be written, and towards a more profound understanding of reality itself. Perhaps time travel isn't about changing the timeline, but about accessing different parts of a timeline that has always existed in its entirety, like turning to a different page in a book or watching a different scene in a movie. The pages and scenes were always there. We just hadn't read or seen them yet. This block universe concept, while still debated among physicists and philosophers, offers a compelling, albeit unsettling lens through which to view our cosmic quest. It forces us to ask not just how we might travel through time, but what time itself truly is. Is it a dimension we navigate, like space, or something even more fundamental to the very fabric of existence? Does our conscious experience of now simply represent our unique trajectory through this timeless landscape? The implications are staggering. If time is a static block, then every laugh you've shared, every tear you've shed, every triumph and every heartbreak exists forever. The person you were yesterday, the person you are today, and the person you will become tomorrow are all equally real, woven into the eternal structure of the cosmos. It paints a picture of a universe far more intricate and mysterious than we can often conceive. So, as we stand at the threshold of humanity's greatest dream, perhaps the ultimate challenge isn't just to build the machine, but to truly comprehend the nature of the very thing we seek to master. If time is not a river, but a mountain range eternally present in its entirety, then our journey isn't about altering its course, but about finding a way to hike its peaks and valleys, to see its breathtaking vistas from new and impossible perspectives. It's about experiencing the fullness of what already is. What if the keys Einstein gave us don't unlock a way to rewrite history, but rather a way to perceive the entirety of history, past, present, and future, as a single, magnificent, unchanging truth? What if the greatest adventure isn't just through time, but into the very heart of what time truly means?